Okay, I wanted to do a quick follow-up to the cycling gear part 2 presentation because I don't think I did a great job of explaining how to use this equation and interpret it. So I thought I'd do a quick follow-up. So we derived this equation in part 2, the propulsion force pushing on the bike rider, which makes the bike go forward, is equal to what the person is doing, pushing on the pedal, times d perpendicular crank, which is the length of the crank arm that the pedal is attached to, times the size of the rear gear divided by d perpendicular chain. This is the size of the front gear, and then d perpendicular propulsion, which is the size of the wheel. So I don't think I picked my subscripts well enough to describe, but so I added a second or a final page of notes in your notes, and I rewrote the equation here. I just rearranged things, and I put d perpendicular crank and d perpendicular propulsion right here. This is the crank arm length, and this is the wheel size, and those are fixed while we're riding. Can't change those. I'm riding my bike. I can't do anything about my crank length or my wheel size. I can buy a different bike, I can buy a different wheel, but while I'm riding, these are fixed. They're constant. These are the gears. So this is the rear gear size, and this is the front gear size. Rear gear, we talk about that size in terms of number of teeth. A 28-tooth gear is bigger than an 11-tooth gear. D perpendicular chain is the front gear. A 53-tooth front gear is bigger than a 39-tooth gear. And you watch the bike anatomy and a couple of the videos I put up showing the bike. I'll talk through that. So make sure you watch those videos of me talking about the bike. So I just rewrote this using some more common terms. So here's the propulsion force making the bike go forward. The person force, crank arm length, okay, d perpendicular crank. Wheel size, d perpendicular propulsion. Those are fixed. Rear gear size, this is the number of teeth of the rear gear. Front gear size, again, the number of teeth. And the number of teeth basically determining the radius of the rear gear and the radius of the front gear. So if my rear gear is the same size as my front gear, then for whatever force I'm generating as the cyclist, that's going to translate to propulsion force. So if I'm riding uphill, if I'm doing mountain biking and have lots of difficult terrain to get over, if I'm trying to start from a stop position, I want my rear gear to be the same size as my front gear. And that way, whatever force I'm pushing on the pedal is going to be translated to pushing the bike forward. The downside of that is, thinking of gear inches, for every pedal revolution, when these two are the same size, I get very few wheel revolutions. So if the rear gear and the front gear are the same size, for each pedal revolution, I'll get one wheel revolution, which means my bike is only going to go so far as one circumference of the wheel for every pedal revolution. So if I want to travel a long distance, if I want to go faster, I need to spin my pedals really, really, really fast, which gets exhausting, and that's not a good way to go fast. It's a great way to be to get the bike going or to go uphill. So going uphill or from a stop position, we want the rear gear size to be the same as the front gear size or close to that, so that every force that I generated on the pedal will be translated to a propulsion force. Now, if I'm trying to go fast, I want a small rear gear and a big front gear. Interestingly, that means if this is small and this is big, for whatever force I generate on the pedal, I'm going to have less force generated at the rear wheel propelling the bike forward. So let's just use fictitious numbers. If my rear gear size is 1 and my front gear size is 10, that's 1/10. So if this is 100 newtons times 1/10, this is going to be 10 newtons over here. So 100 newtons generated, or pushing on the pedal, 10 newtons generated to propel the bike forward. That seems weird, but remember, the bike is already moving. Well, let me take that back. If we're at a stop position, what that means, if I've got a small gear in the back and a big gear in the front, I need to push really, really, really hard in order to get that bike going, to generate some propulsion force. And so I don't like to do that. I always try to, at a stoplight, get to a gear ratio where the rear gear is close to the front gear size. Then whenever I push, I'll be generating about the same amount of propulsion force. But when I'm biking fast, I'm going to be in a small gear in the back, big gear in the front. I don't generate as much propulsion force, but for every revolution of the pedal, I'll get multiple revolutions of the rear wheel. So once around in the pedal can translate to 5 times around in the rear wheel, which means I'm going to travel 5 times the circumference of the wheel with each pedal revolution. So if I'm going at a cadence of 80 revolutions per minute, that means I'm going to cover a lot of ground for that 80 cadences, the 80 revolutions. Now, in contrast, if my rear gear and my front gear are the same size, for every pedal revolution, I get the same, I get 1 wheel revolution, which means if I stay at 80 revolutions per minute, I'm going to get far less rotations of the rear wheel, and therefore I'm not going to be going as fast. So if I want to generate a lot of propulsion force for every propulsion or person, every force pushed by me as a cyclist, for example, going uphill or starting from a stop position, I messed up here, big rear gear, small front gear, or close to the same size. Big rear gear, small front gear. If I really want, like maybe a mountain bike will have this, there you can actually have a bigger rear gear and an even smaller front gear. That means that you are really maximizing how much force you can generate at the rear wheel to propel yourself forward. But for every pedal revolution you do not travel a very far distance. If you're trying to go fast, choose a small rear gear, 11 tooth, and a big front gear, 53 teeth. So that you have you generate less propulsion force, but you're already going fast, and all you're trying to do is maintain velocity. And for every pedal revolution, you have multiple rear wheel revolutions, which means you multiply the circumference of the wheel times every revolution, and that tells you how far you're going. And for a given cadence, you'll travel a further distance for that time, which means you go faster. Okay, so hopefully that helps explain it, and maybe using these phrases is a better way to look at this equation. All right, hope that helps. Thank you.